Hello, I am JD and you're listening to The Ongoing. This episode is about an experiment that forced scientists to rethink one of the most basic assumptions about light. For centuries, light had been treated as something made of particles, tiny bits that traveled in straight lines. But one simple experiment showed that this understanding was incomplete. And after this experiment, light could no longer be understood in only one way. This is the story of Thomas Young and the double slit experiment. By the late 18th and early 19th centuries, most scientists believed that light behaved like particles. This view went back to Isaac Newton. In this view, light was made of tiny particles that traveled in straight lines. That view explained everyday experience well. Light made sharp shadows. It reflected cleanly from mirrors, and it bent when it passed through glass or water. There were some other ideas though. Some scientists suggested that light might behave like a wave, but there was no clear experimental result that settled the question. That was the situation in early 19th century when Thomas Young began his work. Young was a physician by training, with unusually broad interests across science. He studied vision, sound, language, and physiology. As a part of his work on light and vision, he decided to test a simple question. Could light show the kind of behavior that waves are known for? So he designed an experiment. Young let sunlight into a dark room through a small opening. That light then passed through two very narrow slits placed close together. Each slit was only a few micrometers wide, about 1/10 the width of a human hair. Narrow enough that light spreading from one slit could overlap with light from the other. Beyond the slits was a screen where the light landed. The setup was simple. If light were made of particles, then particles passing through two slits should produce two bright regions on the screen. That's all. No structure, no pattern. That is not what appeared. Instead, the screen showed a pattern of bright and dark bands. Light, dark, light, dark, repeating across the screen. The pattern was stable. This pattern is called interference. Interference is something waves do. Think of water waves. Every wave has two parts: a peak, the high point, and a valley, the low point. When two waves meet, different things can happen. If a peak meets another peak, they add together and make a bigger wave. If a peak meets a valley, they cancel each other out, and the water becomes flat. This adding and cancelling is called interference. Particles can collide. but they cannot cancel into nothing. Only waves do that. Here's what the pattern meant. Light is spread out from each slit like a wave. Where waves arrived together, the screen was bright. Where waves cancelled, the screen was dark. The dark regions were not shadows. They were places where light destroyed itself. That behavior required waves. Young reached a clear conclusion. In his experiment, light behaved like a wave, something that spreads through space and can interfere with itself. This did not explain everything about light, but it showed that a purely particle view could not explain the result. At first, his work was controversial. But over the next decades, other scientists repeated and extended the experiment. By the mid-19th century, light was widely accepted as a wave. That still wasn't the end of the story. In the early 20th century, scientists began testing light in new ways, very different from Young's setup. In some of these experiments, light did not behave as something spread out smoothly through space like a wave. Instead, it arrived in localized individual events, each interaction happening at a specific place and time. In 1905, Albert Einstein proposed a simple but radical idea. Under certain experimental conditions, light behaves as if it comes in discrete packets of energy. These packets were later called photons. This did not mean that light was a tiny solid object, but it did show particle-like behavior. Light arriving as individual, countable events. That behavior could not be explained by Wave's idea alone. Scientists then returned to Young's experiment with new tools and new technology. Instead of sunlight, they used highly controlled light sources, modern lamps and later lasers, and they reduced the intensity until light reached the screen one event at a time, so slowly that individual flashes could be detected. Each arrival appeared at a single point on the screen, localized, as if something particle-like had arrived. But something remarkable happened. As these individual events accumulated over minutes and hours, the familiar interference pattern slowly emerged. The same bright bands and same dark gaps. Even when light arrived one event at a time, the final pattern was still the same. What this showed was not that Young was wrong. It showed that the story was deeper. In some experiments, light spreads out and interferes like a wave. In others, it arrives in discrete events, showing particle-like behavior. And in carefully controlled versions of double slit experiment, both aspects appear together: wave behavior and particle-like behavior. What stays with me about this experiment is not just what it revealed about light. It says something about how knowledge moves forward. The process of testing, observing, accepting, and revising, that's how science grows. Not by holding on to the first idea that works, but by being willing to change when reality demands it. Thomas Young didn't finish the story of light, but he showed something essential. Progress begins when we let evidence, not preference, lead. And sometimes learning doesn't come from finding a final answer. It comes from realizing that the answer itself needs to be revised. Thanks for listening. I am JD and this is The Ongoing.